So welcome everyone. This is our second prototyping workshop. The first one was laser cutting, which was 2 weeks ago. And this week we'll be doing 3D printing and design. So we'll be learning about how 3D printers work, how to operate one, and also some design considerations and some things that are possible that you can design that only works with a 3D printer. All right, so we can go on to the next slide. All right, so so for those of you who haven't been here, welcome to the Student Startup Center, the virtual version. So basically, our main mission is to try to help all UC Davis students start their ventures, and that could be anything from just learning about entrepreneurship and learning about startups, or even if you have a fully fledged idea that you want to try to turn into a business. Our goal is to really help you do that. All right, so some of the resources that we have are so we have a lot of stuff just from just educational and just kind of discussion type events to more involved business accelerator type events. So some of the stuff we have are classes that you can take for credit that can help you get a certificate of entrepreneurship, and that's those two classes are Engineering 8, which is the theory of more like a lecture style class that teaches you about entrepreneurship, and then Engineering 80, which is launching a business, which is more of a workshop type class where you actually get together in groups and work on trying to solve a problem that you could try to turn into a business. And then Hacking for Defense is another class similar to Engineering 80, except it's the problems that you'll be solving are given to us by the Department of Defense. And the other thing we have is a makerspace with a lot of prototyping technologies. So when we're open, we offer 3D printing services, laser cutting, CNC routing. We also offer Arduino microcontrollers for you to borrow if you want to use. And all of our services are completely free for students. And I think we're probably the only makerspace in Davis to do that. And and as well as that, we also offer workshops to teach everyone how to use all of our machines, as well as other skills that we have, such as a group leadership workshop. We also have VR workshops, 3D modeling, stuff like that. And also we have more entrepreneurial business type events. So we have events that can help you just learn more about entrepreneurship and just how that process works. Just see the different faces of startups, such as Pitches and Popcorn, which is a discussion type event where you watch startup pitches and just kind of discuss them, as well as mentor visits where we get people from from the startup world who's been successful, or maybe they're in the process of launching a business, or they've already launched one, stuff like that. And they come in and talk about the experiences. And also, for those of you who do have a fully fledged idea that you're really thinking about making into a business, we have a accelerator program for startups. So it's a 12-week program where you can work on your project. You get seed funding and stuff like that. And at the end of it, you get a chance to kind of do a pitch competition for even more money. So yeah, so that's enough about kind of the general Startup Center. So this workshop is part of a series of prototyping technology workshops. So we have to start off with describing what exactly is prototyping. So I'm sure a lot of you have heard the word before, but to just kind of give like a concise definition, prototyping is the process to get from an idea to a working product. And it's part of this design thinking process that you can see here. So the process is, so we start with empathize. So empathizing, I'm sure you already know the meaning of it, but basically in this context, it means trying to step in the shoes of your customers or your the potential users of whatever it is you're making, and trying to think of like trying to see what their experiences are and see what they need. And then from there, like just kind of see what sort of problems they might have, which sort of leads into the next step, which is define. And in defining, you actually try to narrow in on one of those problems, and try to define an actual problem that you can try to solve. And that's being very specific with sort of like what are your constraints, what are your what does your product have to do, what does your product have to achieve, what limitations do you have, what possibilities are there, and then the next step is where you actually go in and start thinking of possible solutions, start thinking of possible products, thinking of possible ways to solve the problem that you've just defined. And then once you've gone through those steps, you can get into what we'll be talking about today, which is like the prototyping, which is where you have your idea, you've kind of designed it, and now you can start making the actual physical product, if it is like a physical device. And then from there, so the point of prototyping is to try to get to a physical prototype that you can actually test as fast as possible, like as quickly as possible, so that you can kind of iterate a lot faster. So you see in the graphic there that everything's sort of surrounded by these circles. And what this means is that all of these steps are kind of loop back on each other. So once you prototype and once you test your design, you have to go back and kind of like see what problems it has, and sort of define some more problems, define some more constraints and limitations, and then you have to go back and ideate, and you have to go back and come up with new solutions to your problem. Like, if your idea is like not good enough in some way, how are you going to fix that? And then you just got to keep repeating that until you get to a product that you're a lot more satisfied with. And yeah, so next up we have, what is 3D printing? So 3D printing is a rapid prototyping technology that uses additive manufacturing. So additive manufacturing is like exactly as it sounds. It's manufacturing that adds material, rather than like if you're familiar with like CNC routers and mills and stuff like that. Those are subtractive, because you take a big piece of stock material and then you cut it down to a more detailed shape. The cool thing about 3D printing is you can just every design, no matter how complicated it is, because it's additive rather than subtractive, you don't have to deal with some of the design limitations that subtractive manufacturing has. So the main limitation is size rather than complexity. So as you can see in the picture, you can get this really detailed looking structure, and it will be much easier to 3D print than, say, to try to machine from a big piece of stock material. And it's also very easy to go from an idea to a working prototype because you don't have to think about how to manufacture it. Usually if you're able to design it, say in like a CAD program or something, or like in a 3D modeling program, you're able to just send it to the printer and print it out. And it also makes it so that some sorts of designs are possible rather than some designs that would be impossible in another form of manufacturing, it would be possible in 3D printing. So the basics of how this works is, at least in the printers that we own, which is a fused deposition modeling 3D printer, it's basically a hot glue gun. You have a sort of a piece of plastic that's fed through a tube, and it's heated up at the end and melted and squeezed through. And then from there, you build up layers. So as you can see here, we have, you can actually be your own 3D printer with a hot glue gun and a lot of time and patience. And like, I think from that video, like you have to like keep blowing on it because hot glue doesn't dry fast enough, something like that. But as you can see here, the two processes between the man making the tree and the 3D printer printing the that weird shape is exactly the same. You just lay out some melted plastic, wait for it to cool, to solidify, and then put a new layer on top. And the cool thing, the good thing about 3D printers is that you can use a CNC, which is computer numeric control, which is basically using a computer to do precise movements to help you build your part. And yeah. Next we have, so I mentioned this before. What 3D printing allows us to do is that it makes certain geometries and certain designs possible that you would not be able to do in let's say subtractive manufacturing. So as you can see here, I can make a 3D like a 3D printed fidget spinner that that prints all in one piece. Well, all in one piece as in like all in one print. But as you can see in the cross section, there is, it actually interlocks with itself. And so you can't take it apart, but you are able to have like interlocking pieces that are like you wouldn't be able to cut this out well from like a raw stock material. I mean, you can, like, it might be possible, but it'll be a lot harder to do than just 3D printing it. All right, next we have Summit will go into 3D printing fundamentals.
Cool. So first off, we're just gonna cover some like basic components on the printer itself. So first we have the print display. It's also like the controller where you can like enter the SD card with the files on it. From there, you can select which print you want to start or what temperature you want to set the hot into, so you can load filament, change filament, things like that. You can also preheat it from here, so that way you can like heat it up, and that way when you're ready to start the print, you can just hit print, and you won't have to like wait for it. From there, we also have the extruder, which is just a motor that pushes the filament, that takes the filament that's off to the side on a holder, and it takes that and it pushes it into the hot end, which is the metal end on the 3D printer that actually gets hot. And this is where the filament melts. It reaches like 200 degrees Celsius, and then this entire print head moves around and lays it on the print bed, which is also sometimes heated depending on the printer. There are some materials where you don't need to heat the print bed. It just makes it easier. And like Jovan said earlier, with the hot glue gun analogy, you have to blow on the hot glue to actually cool it down before you can lay down the next layer. And for that, we have a cooling fan, which is like constantly blowing over the nozzle. So as the filament is being extruded through the hot nozzle, the cooling fan is cooling it back down so it can lay more filament on top of it. So some things to keep in mind with 3D printers is that, yes, they can follow directions very precisely, but they're considered dumb machines since they have no idea what's like happening if anything goes wrong. So a general like thought about it is you don't reach inside the print volume while the printer is running unless you know what you're doing. Like Jovan or I may reach into it like to pull out, use some tweezers and pull off a little piece of filament that could cause a print to fail, or like it was just kind of stuck to the build plate. So something like that, since we know what we're doing, we can do that safely while avoiding the moving like the wheels and the belts, and also avoiding the hot end. We can prevent the injury. And the risk of injury isn't super high, but also if you like put your hand in the print volume and it hits the actual print head, it could nudge it out of alignment and mess up your print. So you'd end up with like you'd have your bottom layers and then the top layer just be shifted over however much you pushed it. So because that's because the risk of injury is pretty low because the nozzle is extremely small. It's like I think it's like 3 millimeters across, and it's like hidden by the cooling fan and other stuff. So it's kind of hard to grab that unless you're intentionally going for it. So the basic process of like taking an idea and 3D printing it is you take your idea, you sketch it out however you want to like get the dimensions down. You create a CAD model on your computer, and this file can either be designed yourself or you can find it online from a few resources. Our next workshop will be showing you how to make your own CAD model for 3D printing. From there, you need to convert it into an STL, which is just the what you save it and export the part that you've made. And so STL needs to be converted into G-code, which is what the 3D printer uses as like a instruction set that it follows like line by line for what to do. And this is done by putting the file into a slicer, and we'll go over that in a minute. But basically the slicer just takes up your model, cuts it up into a bunch of layers based off the layer height that you want, and then it saves that into the G-code file where it basically says like, okay, this is layer 1. I want it starting at this XYZ position and moving to this XYZ position while extruding or while not extruding and stuff like that. So so setting up a print. When you bring your file into your slicer, there's like a ton of different options you can actually mess with for your print, like layer height, the infill density, the actual any support material that you're using. And these customizations can affect the print quality as well as like how fast it's printing. So like if I have a thick layer height of 0.3 millimeters, it's gonna print faster than a model with a layer height of like 0.05 millimeters, since that's a smaller transition between each layer. So first I'm gonna go through a couple of examples, and I'll just show you in the slicer how you can take a file and actually modify it. So for the first part of the setup, you bring in your model, and then the first few things you're going to want to look at are layer height, shell thickness, and what is this? Layer height, shell thickness, infill, and then whether or not you want supports and how your print is going to be adhered to your print bed. And then so the settings that will affect the resolution of your print are layer height, and then the ones that affect the actual structural integrity would be shell thickness and infill. Supports and print bed adhesion more help the actual making sure that the print will succeed, as you'll see later on. So here's an example of layer height. There is the first print, which is done at 0.05 millimeters, and that took just over 3.5 hours. And you can see how the layer lines aren't very visible. And then as we move up through the layer heights to 0.25 millimeters, it only took 40 minutes, but you can see that there's a significantly higher amount of ridging, so you can see the layers more. It really depends on what you're going for. 0.05 is usually not used very much, and people use 0.1 at the startup center for like artistic things or like things that need to be like a very precise size, or they're pretty small. 0.25 is a good layer height for like prototyping and just trying out an idea. So because it's pretty good, like there's thicker layer heights, but it's also fine enough and it'll print at a like an average speed. FDM printers can print from 0.05 to 0.35 for the standard 0.4 millimeter nozzle. You can increase this to like a 0.8 millimeter nozzle and get layer heights of up to 0.6, which would, of course, just print faster. Those are for more aesthetics, and from here we're going to shelf thickness, which is more for the structural integrity of your print. The pictures at the bottom are actually the shell thickness, so it's how thick the walls are, so the number of times that the nozzle goes around the perimeter and lays down plastic. So one wall would be like a vase or something if you just want to print it really quick. 2 to 4 layers is a good amount for like aesthetic prints, or just like something that won't have a whole lot of like force put on it. And then 5 to 10 walls is good for like high structure, like high strength parts. And you can really see how much like from 1 wall to 5 walls, like the thickness is being added here. So the next modification for both print time and print strength is infill. And this is done by varying how hollow the actual print is at the end of by the time you're done with it. So there's a few different type of patterns, but they all have different strengths and print times. There's a bunch of tests on YouTube. Some people don't believe it, and they just print which one they think is the best. Typically 25 to 50% infill, the high shell thickness, is like perfect for like prints that need to hold load, or they need to be like structural. And other than that, you'd have like you reach the diminishing returns point where you're just putting in more plastic and not getting that much more actual strength out of it. You typically 5 to 15% is enough for aesthetic pieces. So here you can see like as you increase it by 10, it increases the amount of infill by it more than you would think. So like by the time you get to like 50, it looks essentially solid, but you are missing out on half of it. I would say very rarely is anything printed at 100%. Jovan, have you done anything at 100?
Never. Yeah, no. Like 50%, like someone said, like is basically solid. Usually, like in our physical workshops, we'd actually have demo pieces where you can actually sort of feel the rigidity of these different strengths. And even at 15, like it's already plenty strong enough. Like you can't feel it give at all. And 25 even feels pretty solid.
Cool. So once you have your G code, you put on your SD card if your printer supports that. If not, you have to like plug it in with a USB cable like a normal 2D printer. There's issues with that, but that's mostly if your computer turns off while the USB cable is plugged in, your print will stop. So you'll go to your printer, you're going to preheat both the print bed and the nozzle if you have a heated bed. And then once it's preheated, it'll home to its X, Y, and Z axes. So it's like it knows where 0, 0, 0 is. Some printers do this on the front left part of the print bed, and others do it on like the back corner. There's a few types of printers that just center in the middle of the print bed. I don't know why. So once it's hot and it's homed, it's ready to start the print using the controller. One thing to keep in mind is once it is homed, all of its next movements for the rest of the print are based off a reference to where it thinks home is. So if you like hit the printer while it's homing and it just stops in a different position, it will move relative to that. So once you start a print, you don't just like hit print and walk away. That's bad. You want to make sure the first layer goes down well and actually has a chance of adhering to the print bed. This is done with like a skirt or a brim, and a brim is kind of just you take the first layer and you increase it out so you have a higher surface contact with the print bed itself if you have some small parts. A skirt is kind of like a trial run where it'll outline the part and then move on to printing the final layer for your first layer. You'll use these to actually like make sure your first layer is like in tune, and you can tell you can tell in this image at the bottom where what's too high is you can see through it. If it's too low, it's going to look like there's no filament. It'll be transparent. And just like the perfect amount is, it'll be like squished, but it won't be completely smashed against the print bed to where it looks transparent. And there also won't be like gaps in between the lines if it's at a good height. Identifying these usually takes some like trial and error and like doing it a few times, but eventually you get the hang of it. Sometimes for the most part, you can level a printer once and then keep it in that level for a good 3 to 4 prints. So usually, some people say like 90% of prints will like complete successfully if the first layer adheres pretty well. And this is an example of a print where the first layer didn't adhere, so it actually warped off the print bed, and that's due to the cooling forces. I think we'll talk about that later. So, yep, this is the warping. So how the warping happens is you put down the first layer of hot plastic, and that's going to cool down due to the cooling fan and also just the ambient temperature of the room being significantly lower than the hot layer. And then once you put down the next layer of hot plastic on top of that, the first layer will have already contracted a little bit. The next hot layer is going to contract on top of that cold layer, and it'll just pull off. It'll start doing compression on the bottom layer and pulling it off the print bed. This can happen at any point, like either on the first layer and the layers above it, so it can warp off the print bed, or it can also happen mid-print where it'll just make the layers not adhere to each other. So this will cause cracking in the middle of the print. Usually it's not as common in the middle of the print unless there's some other issues, but on the first layers, when I see warping happen the most. And then to prevent that, you have various bed adhesion tactics. So the first would be just a skirt, which is, like I said, just an outline. This doesn't do much for bed adhesion, but it allows you to dial in your first layer height, which is you can change on the printer like live as the print is going. From there, you also have a brim, which just increases the surface contact area for the print on the print bed itself. So you have if it does warp, it'll warp out at this edge rather than at the end on the part. And then the last option for bed adhesion is a raft. This is basically like it prints like a millimeter of plastic, and then it starts to print on top of that to try and prevent warping. Another reason people use rafts is if your print bed is already like completely messed up from something else, or like your print bed isn't perfectly level and you know that and you can't fix it, your raft will create a perfectly flat print surface for your print on top of it. And then, Jovan, do you want to talk about supports?
Yes. All right. So for supports, so I mentioned before that 3D printing allows you to kind of print basically any geometry. That's partially true in that there are definitely a lot of other considerations for certain geometry that can't be printed with 3D printing, but we can get around that using supports. So basically the logic of it is obviously, since it's laying down plastic layer by layer, you can't start a layer in midair. So you need to kind of build up from the bottom with the support material that lets you start that part at the right level, and then after the print, you can break off that support, or if you have a printer with like 2 extruders, you could actually print with a different material that actually dissolves in a certain solution, so that you can take your finished print, put it in the solution, wait like a couple hours, and then it'll come out like looking perfect. So in your slicer, you can kind of check to see whether your model needs support, because you can usually preview the print, and we'll probably show you this later when we actually show you the slicer, but you can kind of go up layer by layer and see how the print is gonna run. And what you'll see is you'll see a part that will just start in midair, like it'll just try to draw something in midair, and that's when you know that okay, that's not gonna happen like the slicer makes it look like. It's gonna start drooping down and stuff like that. So that's a sign that you need to add supports. The downsides of supports are that it takes extra material and it takes longer to print, and as well as like at the bottom where the support attaches to your print, it'll usually leave like a rougher surface. So the goal is to know how to design your part to try to minimize supports, but also to know how to orient your part on the print bed so that it doesn't need as much support. So as you can see in the bottom picture there, if you try to print that traffic cone sideways, it uses all of that support, and that's absolutely not necessary. Like the only part that's part of the actual model that's touching the print bed is that tiny little sliver on the left there. But if you just turn it right side up, you see that it can print with like no support at all. So to minimize supports, you can do a lot of like really clever tricks to try to minimize how much support you need. So so this can be done both during the design process as well as while you're slicing. So during the design process, you need to understand like what your 3D printer's limits are. Like there's we'll talk about this later with like overhangs and bridges, but you can but there are certain geometries where the printer can print in midair, kind of, and understanding those limitations and putting that in your design will help sort of minimize your minimize the need for supports. And as you can see with our so yeah, go to the next slide. Yeah, so as you can see with this mask here, we can, if we try to print it right side up, it would have required like a lot of support. Summit, do you know how long this would have taken with the support on the left there?
I think the left side was about 2 days and the right side was about, I think, 12 to 15 hours.
Yeah, so you can just kind of see like how much difference in time that makes, because the supports will print at the same speed. You can print the supports a little bit faster, but not that much faster, because the printer can only go so fast. Another thing to consider with print orientation is strength. So you can see in the graphic at the bottom, since the 3D printer prints in layers, it will sort of have a grain, kind of like cardboard or wood or something like that. So if you know your print is going to take load, you might have to consider sort of like in what orientation is going to take load. So basically, if you try to push along the layers, like if you it'll be a lot more likely to kind of split apart, because they're like pressed into each other, so they're a little bit weaker. But if you sort of apply force perpendicular to the layers, then it's going to be a lot stronger. Yeah, so this is what I was talking about earlier, to where like there are ways for your printer to actually kind of print in midair. So those include bridging, overhangs, and so another design consideration would be build volume. That's could be another topic. So for bridging, so you can't print anything that has to start or end in midair, but you can sort of print in midair when it's connecting between two points that are already printed. So as you can see there, with the bowl, you can kind of connect and print an entire layer that over that surface. And while it does it, that one does like droop a lot, which is kind of the like the downsides of printing with bridges. It is able to do it still. So printers can usually print like can print overhangs up to like a couple inches, like pretty reliably. But basically, the longer your bridge is, the more it'll start to sag, as you can see in like the bottom example there. So the other one is overhangs. So the concept of overhangs basically is like the like that picture in the bottom left corner there. So basically, as you print the next layer, you're able to kind of have the next layer kind of overhang the previous one, and as you keep building that up, you can actually make it print out at an angle, and that's a way to kind of print in midair as well. And usually printers can do up to like 50 degrees or 60 degrees pretty reliably, but to play it safe, usually a 45 is like a safe like limit to kind of keep in mind. So like trying to keep all the overhang angles like 45 degrees or less.
One thing to remember is to do overhangs like this, you need to also have like a good cooling fan. So that way it's cooling the layers and they're not overhanging and then drooping down a little bit.
Yep. So the last consideration is build volume. So obviously all 3D printers have sort of like a finite size. Like this is where it's sort of different from subtractive manufacturing. Is with subtractive manufacturing, you can kind of take like a big material, carve it down, move it over, and then carve down the next piece. But with 3D printing, you're kind of stuck with the size that you have. So as you can see, these are two of the 3D printers that we have at the Startup Center, and one of them's like so small that it can actually fit in the build volume of our bigger one. So if your print is too big, it will be impossible to print in one piece. You'll have to split it up and figure out a way to glue it together afterwards. Yeah, so for a general summary, there's with design consideration, you have to consider the size, whether it has overhangs or not, whether it has bridges or not, and then just other considerations to try to minimize support. And that's stuff that kind of comes with experience as well. As you print more and as you design for 3D printing a lot more, you kind of get an idea of like, oh, okay, like I've tried printing something like this before and it didn't work, so I'm gonna try to alter this design to make it work. With slicing, you can think of support density, print orientation, layer height, infills and shells, and bed adhesion. And those will affect sort of, some of those will affect like whether your print will be possible, like whether your print will fail or not. But others are going to like how strong your print's going to be, like the infills and shells, or the look of it with layer height, or like how much time you're required to print. And then with printing, basically the steps for actually starting the print is you have to start by cleaning the bed, and then preheat the nozzle in bed. You have to make sure the print bed is level, and then make sure to watch the first layer, because usually once the first layer prints successfully, the rest of the print usually doesn't have any problems. And then when it fails, you have to consider like a couple possibilities. The most common ones would be either the print warping, because there's not enough contact area on the bed, or the nozzle could be clogged, or just other issues with like bed adhesion, like if the bed's dirty or something like that.
Cool. So I'm going to switch this over to the actual slicer so you guys can see the process of setting up a print. And then I'll show you guys some videos of prints actually running.
So before we get started with that, does anyone have any questions for about like just that entire process? It was a lot of information to kind of go through. Can you just like unmute yourself to say it out loud or type in the chat, whichever one works. All right, awesome, thank you.
Cool. So here we have a slicer. It's a little different from the one we use at the actual Startup Center printers, just because it's what I have installed on my laptop. But in general, all of the settings are going to be the same that you can edit. You just have to find where in this slicer those settings are. So for this, you can just go in and drag in your print. So this is a little maker coin that we make for the SSE that Jovan designed. And so I'll drag it in, and then I can pick on the side like which layer height, like basic preset I want from the slicer. So generally what we do is I do 0.2 millimeter speed, since that'll print a little bit faster, and I never saw any difference in the quality one. If it's some like rough part that I don't really need to look nice, I'll do like 0.3 millimeter draft. From there, you select the filament preset. PLA is what we print in at the Startup Center. And here we can check if we want supports or not. So we're gonna leave them off for now, but I'll show you what it looks like if we turn them on. And from here, we can check the infill. Like we mentioned before, 20 is pretty good. Like if we drop this and it's at 20, it won't break. It probably wouldn't even break at 10. And we can turn the brim on or off. By default, this will print a skirt on this software, just that's how they have it set. And at the bottom, I can hit slice now. It'll create the render of what the layers look like. And I can scroll through to make sure every layer is printing right. So you can see the first layer has this outline, which is a skirt. Then it starts the layer itself. And this print, kind of like that fidget spinner, shows how like you can print interlocking parts. Whoops. You can print interlocking parts. So that way the inside and the outside are two separate pieces by the end, but they're like joined together. You can't get them apart, and there's no other manufacturing technique that will allow you to make this. And now you can see how long the print will take. It'll take roughly 3.5 hours. So let's say I turn on supports. And you can see now that it's generating supports on these overhangs, just where it's rounded over. Personally, if I were printing this, I wouldn't use these supports just because they're not really doing anything at that point. They're more of they more add time that I would need to actually remove those at the end. Then when you're done, you have your settings all good. Or if you want to make any extra changes, you can go into print settings, like manually change the infill and the pattern. So we can pick from a variety of these. There's so many.
Show them the gyroid one. That one's pretty cool.
Yeah. Gyroid. So gyroid is just a different type of infill. It's just a shape. It's more of like this cool 3D effect. Some people think it's actually stronger because you can see it's just one shape that's like rotating about as it goes up. So it has strength in all directions. But there's other people don't like it because as it's going, it's like shaking your printer back and forth for no reason. I think it's fun to look at. We can modify how big the skirt is, how big the brim is. We can change the support infill, so the support settings, speeds, any advanced stuff. We can always go in and change filament settings too. Like, let's say I want to customize my filament. Like I know it works good at a specific temperature. I can go in and just change that here. And this is just basic printer settings you set up once, or that come preset. But generally, here, whatever options you pick here will be good enough. You don't have to go into these other tabs. Cool. So once we have it, we'd export to G-code, and then we'd save it to an SD card, take it to the printer. And then this is an example of one of the prints. So you can see it's laying down the first layer and it's doing it pretty well. So I'm not really concerned about this failing. And you can see the extruder motor is right here. And then this is a cooling fan. I think we'll try and get, the other one has a better angle so you can see the actual hot end. It's just kind of inside of that. Okay, here you can kind of see the hot end in there. It's that sliver of metal kind of peeking through. The printer, the style of this printer kind of has it inside this enclosure so that when the fan's blowing over it, it kind of keeps the air located around the hot end and it blows out the other side. But this is the first layer happening right now. You can see it. It printed a little test strip out here to make sure it was extruding right. Then it did the skirt for, so you can check for the actual level of the build plate, and then it'll start the first layer. So this would be something that you'd want to make sure finishes completely before you walk away. And then you can, once it's successfully started, like the second layer, you can probably like stop paying as much attention to it, but you really want to watch the first layer like fully until it's completed. And skip forward a little bit. This one's printing the infill now. I think that was about, honestly, like 15 to 20. I don't remember exactly, but that part is extremely strong. It was just a keychain. And then, so once it's done, the printer will just take the head and move it in the back of the printer. So that way you have full access to the build plate and you can take the parts off without worrying about hitting the print head. And also this little strand right here is, it just happens when it retracts. It'll still have a little filament left in the nozzle, and when it moves away, it just kind of creates a little string like that. One of the good things about it moving away from the actual print is that heat from the nozzle won't radiate onto the print while it's just waiting for it to cool down, so you can make sure nothing gets any warping or any issues with that.
All right.
Cool.
Yeah, thanks for coming.